Thank you everyone for coming to my talk on artificial intelligence and what is needed to do that successfully at a mine site. Before I get started, I thought I would briefly introduce myself. I'm a mining engineer by training. I have three degrees in mining. And besides the degrees, I've also worked in mining, both in surface copper and in underground coal. And for a long time now, I've also been an academic researcher and consultant. I'm currently the Malcolm McKinnon Professor of Mining Engineering at the University of Utah in the USA. I see myself as a mining engineer who learned AI. I learned AI a long time ago in the 1990s, long before it was cool. And back then, deep learning was just neural networks. It was not yet rebranded for sales purposes. But before I get too far ahead, I thought I would acknowledge that there's a variety of skill sets in the audience today. I know some of you are subject matter experts on AI, and hopefully you will agree with some of the things I say, and perhaps there'll be some disagreements as well. And some of you might be on the other end of the spectrum, quite new to AI and curious. And so what I have tried to do is cover topic that'll be of interest to many of you, in that entire spectrum. So first thing I will do is provide some personal clarifications of AI and what I think it is. And then what I want to do is cover some typical applications in mining, some of the success stories. And then I just want to go over some of the challenges that you typically find in industrial applications. And by that, I mean in the mine sites, for example, when you try to do that, and what solutions are out there for those challenges. So first, AI is a very big word. It's very loose. It means many things. It means machines. It means software. And within the software or data realm is machine learning. It's just a subset of AI. And a particular subset within machine learning is deep learning. So that's just the terminology. I really didn't want to go into defining AI. I think most people understand it's the ability of machines to mimic humans' problem-solving ability. But the key word is the intelligence in artificial intelligence. It implies there is intelligence. Actually, there is no intelligence in artificial intelligence. It's all really stuff that we program in, things that we have anticipated, so on and so forth. So there is no real intelligence currently. And the AI that we have on board now can only solve problems that humans can solve. That's it. If humans cannot solve it, your AI will not solve it. So what does that mean at a mine site? So at a mine site, you have a goal you want to achieve, and you have collected data or identified a particular factor that will help you achieve that goal. You have perhaps identified one other factor or two other factors. And so these are the factors that are important to achieving the goal. Now, if there is a fourth factor that is important, AI will not tell you that because AI does not know. AI was programmed by a human being, and that human being anticipated three factors. So that's all that AI can do. But that makes it seem like AI is trivial. It's not. There are a lot of things AI can do really well. For example, within these factors, it can do permutations and combinations of the factors, for example. It can even tell you when factors are not very useful. So all of these are quite useful in achieving the goals. It's just not what we think it is as something all-encompassing in its abilities. All right, so now with that short clarification, now let's go straight into applications. So I tend to think of AI applications as of being one of two types. One is the bounded problem application. This is, imagine you're in a dark room, or you're entering a room that is dark and there is furniture, perhaps in your house. You know the layout of the furniture. You don't know exactly where it is. You know roughly what the parameters are. And really all you need is a light switch. If you can turn on that light switch, you can navigate around that room very well. So what are these types of problems in mining? This is where the key factors and physics are known. You know, you understand the process really well. You have lots of relevant data, and the data quality is not bad. For example, mill optimization problems. Mills are very well instrumented these days and have been for a while. And yeah, so when you find, what do you need to optimize it, a lot of that information is already there. And all you have to do is turn on the light, which in this case is machine learning tools. And your classic, most machine learning tools work quite well with a little bit of preparation. So these are bounded problems. Let me give you an example of one. This is from many years ago, one of my first applications, industrial applications, many years ago at Fort Knox Mine in Alaska, where power is very expensive. And so the question that the mine had was, what impacts the power consumption? What are the factors? They identified 15 parameters that were important. They gave me tons and tons and tons of data on those 15 parameters. We developed an AI model. The model did really well. But what was interesting was we realized that out of the 15, maybe 4 or 5 parameters were useful. The others were not. So we had a big meeting. And so this was discussed, and they were surprised that all the other parameters were not important. Why was that? So when they went and they did due diligence, they realized that a lot of that data from this other sensors, they were not good data at all. So in doing the AI, the model realized that that data was not actually affecting the horsepower one way or another. It was garbage in, garbage out. So the AI was successful in that, in identifying bad data indirectly. And then on deeper learning, they also realized that some of the data was not bad, but actually when you think and you combine all the various parameters, perhaps they do not impact the power as much as they thought it should. So we developed this AI model, but deep learning is difficult to implement. In fact, it is not intended for real-time application. So what we did is we took the understanding that we had from that AI model, and then we deployed a machine learning tool in real time. So what we did is we inserted some code into their process information system, the PI system, and I'll show you what we achieved. So this is a screenshot of that. And so there's lots of plots from my models that we were tracking. And yeah, let me show you this blue line. This is basically our power consumption prediction, 10-minute ahead power consumption prediction. That's the blue line. I drew it by hand on top of the actual plot, so it's more obvious. Now, the real life horsepower consumption, which happened afterwards, was the red line. So you can see that the machine learning was actually quite good as it was observing the different parameters. It predicted that horsepower will go up slowly. It even predicted the jump, the blue line. So the red line came after the blue line. So this is very good, quite successful, and it helped us understand something about the process. Now, let's look at the other type of problem. These are what I call the unbounded problems. So you're looking at this maze, and you don't see anything obvious. Where do we start? Where do we end? What is the pathway? It is not really clear. These are the types of processes where the physics may be known or expected. You gotta know, you have some idea, but it's tough to quantify the various things that impact the process. You have some data, you don't know if you have all the data you need, so you're not sure there. And then it's also possible that the data that you have, you're measuring parameters that are difficult to measure. And so you don't know if the data quality is there. Okay, what is this typical problem type? So when you look at a mill, for example, and you want to know how a particular rock affects throughput. So now you're starting to look for hardness and other parameters like that, or even particle size, where, from a camera, you get a good idea of the surface, but not all of it. So you have some idea, but not really. And so this is an unbounded problem. And so the only solution here is you have to manually look at different aspects of the process, different data streams, slice and dice it, do analysis, and you do it. So in this case, if you deploy your machine learning tools, the canned products, your Python programs, you will be in a bad shape in all of this. So let me give you an example of this. This is a current project my team is working on, and it's with a large American mining company. It's a polymetal mine. They perhaps mine 10 to 15 types of rocks typically. And so their goal was, hey, provide some mine to mill insight. How are these rock types affecting mill throughput, so on and so forth. And we have tons of data from geology, process, dispatch systems, all kinds of data, text data, visual data, graphics, all that stuff. So here's the thing, the bottom line. Here you have your mill throughput. Ignore the valleys here. Those are just when the mill was not operational. I'm just showing a snapshot here. So yeah, the production went up and down. But why? Why did it go up and down? That's really what we want to know. You are sending so many different rock types. So one of the first things, and you will see this here as well, if you directly try to relate your throughput to rock types, it will never work. There are a lot of problems there. So we wanted to find a statistic or some soft sensor that we could design that was very well related to the throughput. So it's not the throughput, but it's an indicator of the throughput. So we called it the mill efficiency or productivity. And so it took into account how the mill was running, operational settings, the duration the mill was running, so on and so forth, various decisions. So incorporating all of that, we came up with this blue line. This is the mill productivity. And you can see the way we did the productivity was pretty good because it tracked the mill throughput. So whenever the productivity was good, the mill production went up. Okay. But the blue line does not have anything at all about rocks. It's simply how the mill was run. And we know that mill is run according to the type of rock that is being worked on or being processed. So now we come to the second step of this. So what we did was through analytics, after all this slogging, if you will, we came up with a parameter called rock character. And so the rock character tries to capture, based on the data, when a rock is difficult to process and when it is easy to process. And so based on that understanding, we developed this tool. And now we have a rock character data stream, if you will, a soft sensor. And when the rock character goes down, that means the material is easy to process, soft rock, easy to process. When it goes up, it is hard rock. So that's what this means. So now the next step of the proof is, okay, so now we have rock character, we have mill productivity. How are they related? Aha. That's your gold line. And you can see when your curve, the blue line is going down, that is rock is getting soft or easy to process, mill productivity is going down. Now, if you were to overlay throughput on this, you will realize it has nothing to do with throughput. So these are sort of two independent parameters that we are capturing from the data. They are not directly throughput or rock type, and we have it. And you can see that whenever we have more, the rock character is harder, mill productivity is actually going down. So, and because mill productivity is directly correlated, highly correlated to mill throughput, we have linked rock to throughput. Okay, so I kept saying that you cannot really look at the throughput directly. Why? So when you start doing correlations and other types of analysis that is typical, you will find a lot of spurious correlations, a lot of bad relationships. So sometimes you will see this rock is positively correlated to throughput. The next moment it is not. So which one is it? So you see a lot of misleading conclusions that way. All right, let me talk about another one. This one was also interesting. This is, I can name this. So sometimes you can name a mine, sometimes you cannot. It all depends on the contract. And so at Erdenet, we had a large contract. We looked at from grade control, from blast hole sampling, all the way to material flow to the mill. And so how does that work? So at first, we did blast hole sampling, and we estimated the sampling error. And so once we understood that, we made recommendations on sampling. Then we looked at the blasting, and we did a blasting study and several blasts, and we tried to see how the material was moving because they had some unique ways to blast, and so we're measuring for that. And so we did that. But really, what is most topical to this talk is the AI that we did in tracking the material. So like all large mines, they want to know how the material that you mined today and you sent to the crusher today, how that, when that gets to the SAG mill, because you want to do grade control with that. Okay, fair enough. So here is their process flow sheet from crusher to the mill. So the crusher is right where the trucks are, and the bottom left is where the mills are. But look what's here. There is one stockpile, stockpile one, large stockpile incidentally, then a second stockpile, and then a third stockpile. Aha. So now, how does it matter what you dumped into the crusher today? When will it get to the mills? That's the question. And so this is what our analytics project was about. This was the part 3 of our project. How do the 3 large stockpiles affect material flow? So again, this was very, very difficult. It is one of those unbounded problems. But eventually we figured out it takes about 2 to 3 days from crusher to mill. But what was more interesting was not this. It was the fact that when we were doing analysis, we realized that we noticed some odd behavior, relationships, and we looked into it, and we found that some of these conveyor belts, they were sometimes going to different locations, so the destinations was changed. And so you know what? In a data stream, you will never know where that tonnage went, and so you had to keep track of a lot of these things. All right. So speaking of challenges, so now I will go to the next phase of the talk, which is challenges in your typical AI project. So first thing is how projects start. So far, many of the projects I've done, they are like this. What can analytics tell me given all this data? I talk to a lot of VPs of technology in mining, and they tend to think of analytics this way. The problem with that is if you start with this type of approach, you will have a bloated budget because you don't know what you're chasing, and you will waste a lot of time. I will say another time, but the first step in all analytics project, the first result is depression. And so, yeah, we don't want that. And so what is best done is start with a well-defined problem. Start with a narrow problem question, the one you're the most prepared for. Start with that, do your analytics, and then you will realize the scope will grow very naturally. These always yield the best results. Everybody knows now that data quality is a challenge. Okay, so that is a challenge, but why? Think about this, okay? The physics, so think about the physics of measurement. If you're measuring the grade the metal content of a large piece of rock using XRF on top of a bucket, why do you think that is going to be correct? Or even take weight. How do we measure our weight in the bathroom? We stand very still and we take the weight. But you know what? Your conveyor belt is not still when you're measuring the tonnage. Neither is your truck. So you know what? The weight measurement is actually one of the most basic and also one of the most erroneous at mine sites. Okay. Second, physics aside, think of the pH, the measurement of pH. Why is pH measurement going to be accurate in all the operating conditions you have? So the physics or operating environment of the sensors are very, very difficult. And so we have developed technology for Sumitomo to try to figure out when some of these sensors go offline or are starting to stray. Offline is easy to detect, obviously, right? But the big thing is also that sensors are not calibrated. I used to be a foreman in a mine. The only time I had spare mechanic was if it was for regulatory purposes. So your quality control, your this type of optimization type of sensors are rarely ever calibrated. In the United States, the oil industry loses, I think, $20 billion a year or so just on sensor issues. Wrong data from sensors, data that looks correct, but it is not correct. And I see a lot of that, right? Second thing with the data, know what you're looking at. Tonnage on one conveyor belt, tonnage in another conveyor belt. In one case, it is dry tons. In the other case, it is wet tons. Did you know that? Perhaps you didn't realize. Perhaps your team did not realize. You will see issues like this. And then if it is wet ton, what is the percentage moisture? Do you know? Do you not know? All of this will create problems. And then whenever we use some sort of like a LiDAR or something and you're computing tonnage from the volume, what is the actual density? And yeah, at one mine, we found after we did all of this, there was a discrepancy of 10,000 tons of copper every year, 10,000 tons. So you can say it's climate change and there is a lot of copper in the air, but that is what happens, right? So I tell my students that in mining, you will not get your rear end kicked by calculus. It's basic mathematics, volume divided by density, volume multiplied by density. Simple things like that are challenging in mining. Okay, carrying on. More data results in better analytics. Wrong, it does not. More data basically means if you do not know what is important, if you do not guide your AI, you will be lost. And certainly, given that your most of your data streams are probably not very good, more data does not result in better analytics. You need a lot of good data, all right? The other thing with data is that when you start a project like this, you have variety of data sources. You will realize nobody understands the entire data picture. Nobody at the mine will do. There'll be 4 different departments. Even within the department, they will not understand the data that they themselves didn't help create. So if an engineer worked there only 2 years, they know what happened in those 2 years, but not what happened 3 years ago. With mergers and acquisitions and all of this happening, this is really, really very hard that nobody understands. And then the other thing that happens is you have a data source and data is being created, but the data that you get depends on the person who extracts the data for you. If 2 different people give you data extracts, there'll be 2 different data sets. And it's interesting, I'm facing this issue at this moment. So all of these are real issues with data. Solution. The biggest solution to all this is communicate. You have to constantly talk to the people who are the closest to the data, go deeper and deeper in that, okay? That is one. Then you select your data carefully, the one that you will analyze. So what we do is we use all kinds of data and then we routinely discard. So my joke is you give me all your data and I will do my best to throw away most of it. I will use very small streams of data. So I tell students it's a big data project in the beginning, but when you do actual modeling, it's a small data project. And that's really what happens, right? And so select your data, understand it, see what it is, dry tons, wet tons, all those complications, verify as much as you can, and then start your work. So, and then you realize that you will always have problem data. So if you throw away all your problem data, you have no data. So your analytics project ends that day. So uh, can you do your analysis in a way where you can handle some of these data issues? Can streams be combined? That's what we did. So when you looked at the ROC and the mill throughput, we used different types of data streams where we had more confidence. And so you can say that some analysis is good for this, some other analysis is good for that, so on and so forth. So design your analysis considering data quality. Challenges. So the National Academies of Sciences, which is a very, very prestigious group that advises the United States government. So they had a workshop a few months ago on analytics. So what can the United States do to better take advantage of AI? And leading the discussions were managers from from Google and Microsoft and all the technology companies. And so soon, of course, one challenge is people, skills gaps. So what did they say? They said, you know what? There are one of the biggest challenges in deploying AI is that you have domain experts. These are subject matter experts, mining engineers, geologists, so on and so forth. And then there are analytics experts, people that know every kind of analytics technique and so on and so forth. And between the two, as you can see, there is a big gap, right? And so what happens? So what happens when you have this big gap? Well, analytics projects will always detect relationships and make conclusions. And when you have this big gap, they will always end up in the wrong places. There'll be quite a few wrong conclusions. And this actually, you see that happening more and more in mining, right? And so where we have been successful, my team is all mining engineers who are highly trained in analytics. So we have one leg in both places. So we bridge that gap. We know the questions to ask. We have taken our geology classes. We have taken the mineral processing classes. So we have all of that background. But that aside, this is actually duplicatable in a mine site. So the best thing I say is train your domain experts, the mining, geology, processing. You actually don't need to use every analytics tool set. So training the domain experts on analytics is a lot easier than sending the computer science people to geology classes and mineral processing classes. So we have training modules in 40 hours. We train domain experts in core analytic skills, easily done, right? All right. The other challenge that you face is expectations. And so AI is thought of this magic. You start doing analytics and suddenly now you understand all the nuances of your process. Well, that's not true. In fact, good analytics is labor intensive and it is interdisciplinary and it takes a lot of time. It is very slow. Automation will happen. You will get there. That is the last stage. So the biggest thing is expectation management, to tell the bosses, hey, this will all happen slowly. This will unfold. And the other thing that people don't understand always is that it requires maintenance. No analytics model or a relationship will last forever. So you have to keep doing this constantly to keep it up to date. Think about all the fundamental changes that happen at an industrial site all the time. So when you change something in a big way, well, your analytics models also have to change to reflect some of those changes that you have made. And finally, we come to the conclusions stage. So, we are at an age of hype. This is much better than what it was 20 years ago. 20 years ago, when I went to a mine site, they gave me a cup of coffee, they gave me lunch, then they gave me a t-shirt, and then told me to go away. Now they actually know that AI is not an academic topic. It is actually doable, and mines are doing that. But what happens is there is this hype, and so they spend a lot of money, they start doing a large scale project, and then the first result of all this is depression, because you start realizing that your data is not good. So there's a lot of bad news up front. You know what? The challenges exist, but they are not insurmountable. So I always pick and choose where I start. So when a mining company comes to me, I always go to the easiest spot where I can start and then let that project grow. And that is much better a way of doing it. And then, success, you will see success will lead to major benefits. You get some really good nuanced information, but the key is slow down, thoughtful, interdisciplinary approach, lot of communication, and it works really well. So with that, I'm really done, and I'm ready for questions.